We're moving on to chapter 32, which we're going to split up into 3 different lectures. And this subject of this chapter is magnets and the magnetic field and magnetism in general. So the way Knight talks about this is he starts talking about just some of the characteristics of bar magnets. And so one characteristic of a bar magnet is, and so we'll see that a bar magnet is very similar to a compass needle. Okay, a bar magnet and a compass needle will align itself with the magnetic field that's around it. And so to make kind of a compass at home, he puts a bar magnet on a little cork in the water, and that'll actually line itself up and point north just like a compass does. Another characteristic is that bar magnets have 2 poles. They call this the north and the south pole. And like poles repel and opposite poles attract, like in the picture here. And then he makes the comparison here between a pole and a compass needle, and you can see that it's essentially, a compass needle is a little tiny bar magnet. And so his characteristic is to use the shaded in region as the north, and then the clear empty region as the south. Another aspect of magnetism is that some things are affected by a bar magnet. So for instance, here he can pick up paper clips with the bar magnet, either end of the bar magnet, but then say for instance a penny is not affected. And so the materials that are affected we call magnetic materials. And finally, an interesting thing here is that if you try to isolate the poles, okay, the north and the south, so here they're trying to get smart, they're cutting the bar magnet in half. What happens, instead of getting a north and a south end, you get 2 smaller bar magnets. Okay, so it's a principle. You can't actually isolate the north or the south. They always come together. So this is one place where it's very different than electricity. You can have a positive or a negative charge, but you can't have a north or a south pole all by itself. So he then sums up sort of all this stuff. And so magnetism is not the same thing as electricity. It is a long-range force. Okay, the bar magnets can pick up those paper clips. All magnets have 2 poles, and they behave sort of like charge, where like poles repel and the opposite poles attract, but they cannot be separated. And you can tell which side it is using a compass. And then that's the last part, is that we call magnetic materials materials that are affected by a magnetic or a bar magnet or a magnetic field. So the next step, he talks about the idea of a magnetic field, which is very similar to an electric field. So here we have a bar magnet, and the way you can map out the magnetic field is to put little compasses in here. And so you see that first of all, the distance away, so that the length of the arrow sort of tells you how strong the magnetic field is. So here between these 2 points, you can see the magnetic field gets weaker as you get further away. And it gives you a sense of how the magnetic field points. And so now we introduce the B field, which is our short way of writing the magnetic field. So we don't have an M field, we have a B field. And it's just convention is why we call it this way. And basically it works very similar to an electric field, and we like to think about it as the force that magnets apply on each other can be described as the interaction between a magnet and some other magnet's magnetic B field. And we like to draw lines with this, just like we did with electric field. And the way the lines work is the direction of the magnetic field is tangent to the magnetic field at any point of these lines. And then the number of lines per area is proportional to the magnitude of the B field. And so here's a picture of that same bar magnet where we've connected all the different lines. And so here, these lines are very close together versus over here. And so it's much a stronger B field over here than over here. And then the actual magnetic field itself is tangent to any point. So if we wanted to find the magnetic field at this point here, it would be tangent going off kind of like that there. And here's just a demonstration of the magnet that influences us the most, which is the Earth. And so the Earth, it's sort of like there's a big bar magnet buried in the Earth. And so here's the Earth. And what's interesting is what we think of as the North Pole. Okay, so here's our magnet. And so the North Pole will be up here, and then Antarctica is down here. But the actual magnet that's inside the Earth is opposite of what we think. Okay, if we're on the Earth, our magnets align themselves with the magnetic field lines, and these lines tend to go from north to south. And so what we call the North Pole is actually a south magnetic pole, and the opposite is true for the South Pole. And so he talks a little bit about magnets, and then he gets into historically how people learned about magnetism. So they knew about bar magnets for a long time, but it wasn't until 1819 that people realized there was a connection between electricity and magnetic fields. And Ørsted discovered that a current-carrying wire causes a magnetic field. It causes a compass to turn. And so here's a little picture. There's no current here. The compasses are kind of hanging out. When the current turns on this side, you can see there's a magnetic field that sort of points in a circle around the wire. So we're going to start by talking about this magnetic field for a while. And here's a closer-up picture. Now, one thing is we're going to do a lot of pictures where we need to talk about things in 3 dimensions. And so we have a way to write something either coming out of the screen or into the screen. And it's sort of like an arrow. And so if you cannot imagine an arrow, okay, an arrow has a sharp point and it kind of has a feather end. And so here, a little dot inside a circle is sort of like the tip of the arrow. So it's kind of like you're looking down an arrow. So that's something that's coming out of the page. Now the back end, if you look at the feathers, you might see an X like this. And so this is the feather part. And it signifies something going into the page. And so here's a current going into the page. And you see what happens is these compasses align themselves up in a circle that's going in the counterclockwise direction. And so we introduce what's called the right-hand rule to sort of talk about this. And here's the right-hand rule. And so the way it works is, first of all, use your right hand, and your thumb goes with the current. And when your thumb goes with the current, your fingers coil around the way the magnetic field would be coiling around. So in this picture here, if you take your right hand, if your thumb goes into the screen, your fingers curl around in a clockwise fashion. And that's what the magnetic field does. Here's a kind of nicer, clearer picture of the magnetic field. So the magnetic field is circles that circle around the current. The direction we get from the right-hand rule, and we'll get the numbers later from an equation. But this is how it looks. And you can see here that basically the spacing gets closer together. So the lines here are closer together than out here. And so the closer you are to the wire, the stronger the magnetic field is, which hopefully makes sense. And to calculate this with numbers, we use what's called the Biot-Savart law. This is probably one of the worst equations I'll ever show you. Apologize for that. We won't use it too much, but this is the magnetic field from a point charge. And it has some similarities to the electric field from a point charge. If you remember, that looks something kind of like this right here with the direction, the absolute value of it looked kind of like this here. So it had a constant in it, it had the charge. One thing is that the magnetic field depends on velocity. So only a moving charge will make a magnetic field. It also, on the bottom, depends on r squared, similarly to the way that electricity does. And so we use this to figure out the actual size of the magnetic field. Here's just a little talk about that constant, that U-naught constant. So it's kind of ugly. It looks like this here. One little hint is that oftentimes your U-naught will be over something, like for instance, it's often a lot of times over 2 pi. And so in that case, you can cross out the 4 pi that's in there with the 2 pi, and this number is actually then just 2 times 10 to the negative 7 Tm divided by A. The units for magnetic field is the Tesla, which looks like here, 1 Tesla. And here's just the magnetic field of some common things. So generally, magnetic fields we deal with are very, very small. In a laboratory, in a physics laboratory, a really big one would be about 10 Tesla. So that's a pretty large number, actually. Now the book takes that Biot-Savart law and calculates the magnetic field caused by a current-carrying wire. So here's a little picture. Again, if we use our curly right-hand rule, I sometimes call this one the curly right-hand rule, with this current here. So the current, you can see that it's coming out of the page, and so if you point your thumb with the current, your fingers coil around in a counterclockwise fashion. So that's how you get the direction. And then the actual magnitude you get from this equation here. So it's another case where you got U-naught over 2 pi. And so we're going to use this and the direction to learn a little bit about the magnetic field. So let's give this a try here. So here we have a current carrying wire, and there's 2 points, A and B, different distances from the wire. We want to know something about how you compare A to B. So give this a try and we'll talk about it. Okay, so comparing the field at point A to the field at point B. Hopefully you got that it's half as strong and in the opposite direction. So our equation for B field, just the magnitude of it, is this equation here, where it depends on 2 pi r. R is the distance from the wire. So here would be the r in the case of A, and here would be the r in the case of B. And so r of B is exactly twice as big as r of A. And so that means it'll be half as strong at point B. And then the direction, okay, so now we get another chance to do our right hand rule. If I do my thumb pointing with the current, all right, the tendency is then for my fingers to be pointing out over here and in over here, kind of in a circular motion. Think about this one. This is tricky. The right hand rule can be very tricky to visualize sometimes, but if my thumb goes with the current, my fingers come out on the left and go in on the right. And our last thing here is now, instead of looking at a current, we're looking at just one piece of charge. But again, you can think about them as kind of the same thing. So what is the direction of the magnetic field at the position of the dot, which is right over here? Here's our dot, caused by this proton that's going into the screen. So think about this and then let me know what you think. Okay, so hopefully you got up. So again, in this case here, what's sort of happening is I have, since there's a positive charge going into the screen, my current goes into the screen. And so this point over here, if I draw circles around this, that's not a very good circle, sorry. But if I draw a circle, if my thumb goes into the screen, my fingers curl around in a clockwise fashion. So it's clockwise fashion. And so at this point right here, all right, it would be pointing upwards. Just like if it was a point over here, it would be pointing downwards. And if it was a point over here, it would be pointing to the left, all that kind of stuff. So the answer should be up. This is tricky to do on our video. We're going to talk way more about this in class on Wednesday, but look at the book and try to do a couple of these examples with your hand and make sure that it works.